join ചെയ്തിട്ട്
Good evening, sir.
Good evening, sir.
Good evening, sir. Can you share the screen, sir?
Okay, sir. I will post you 1 minute. Wait, sir.
Okay.
Okay, sir, you can share the screen.
Good evening.
1 minute, sir. Wait, 1 minute, sir.
Good evening.
Hello, sir.
Oh, okay. Sir, I will join through mobile phone also. Yes, sir. I will join through mobile phone also, so that I
Okay,
can
sir.
see the comments.
Okay, sir.
Sir, I will join.
Recording in progress. 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 Recording in progress.
Yes, sir. So, welcome you all for strength of materials review session. So, whatever we have discussed in the previous classes, right, in the offline classes, based on that, you have solved so many previous year questions. You have attended the examinations also. Examinations conducted by our ARC. So, welcome you all for strength of. Then you may have some doubts. So whatever we have discussed in the previous classes, right, in the offline classes, based on that, you have solved so many previous year questions. You have attended the examinations also. Examinations conducted by our ARC. So welcome you all and pursuit of. Then you may have some doubts. Getting reverse audio. So whatever you discussed in the previous classes, right? In the offline classes. Sir, it's getting voice back. Is it audible? Is it audible now? Clear? Yes. Okay. Great. So we will go through the small fundamental informations. Okay. So that will help you to again go through the previous year tough questions. Okay. So first, I want to discuss with the stresses in beams, second chapter. Okay. Second chapter, stresses in beams. That is very, very important. Right. Sir, in the second chapter, what we are going to study? Second chapter, very, very big chapter in the strength of material. Okay. Right. Now, okay. Now, okay, audio. Yes. Okay. In the second chapter, we are going to study support reactions. Support reactions, shear force diagram, bending moment diagram, bending normal stress due to bending moment, transverse shear stress due to shear force, slope, deflection, strain energy, natural frequency. These are all coming under beams. Okay, these are all coming under beams category. Okay. So what are the possible questions in beams are? 9 questions are. Is there any weightage? No partiality. All are having equal weightage, top to bottom. Okay, right. Okay, so in case of simply supported beam, we must start with the support reaction. We must calculate the support reaction, then only we can go to remaining calculations. In case of cantilever beam, without doing the support reaction calculation, we can calculate the remaining, sir. In which beam? In cantilever beam. The condition is we have to start the calculations from the free end and we have to move towards fixed end. Okay, that is a condition. If we are doing so without calculating the support reaction, we can draw the SFD, BMD, bending normal stress pattern, shear stress pattern, slope, deflection, strain energy, right, everything. Okay, but in the strength of material, up to here, right, we are studying in the second chapter. This is studied in the fourth chapter. After the torsion, you will study deflection of beams, right? Sir, strain energy, sir. Strain energy also included in the deflection chapter, because with the help of Castigliano theorem, we can calculate the deflection. Okay, right. Then we will study the natural frequency in transverse vibration. What is a transverse vibration natural frequency formula? F1 is equal to 0.4985 by square root of delta. What is delta? Deflection in meters. Deflection in meters. Okay. Sir, what is the unit? Final unit hertz. Okay. Right. Sir, many times they have asked this question. There is a special question also. There is a special question also. Right. Sir, which type of question, sir? Critical speed or whirling speed? Critical speed or whirling speed? Right. Sir, what is the formula for critical speed? NC equal to F1. That's all, finished. Okay. Sir, what is the unit for F1? Sir, hertz, sir, hertz. Right. This is hertz. Right. Hertz means what? Cycles per second. It means revolution per second. It means RPS. RPS. So it is very difficult to communicate the RPS values to the machine operators. They may confuse. Then what to do? We can convey through RPM, sir. RPM. If it is RPM, easily they will understand speed, right? Then how to convert the RPS into RPM? Sir, into 60. Into 60. That's all. Okay. So NC is nothing but critical speed or whirling speed. NC is nothing but natural frequency in RPM. That's all. Very famous question in the vibration, repeated question. So that is coming under transverse vibration. Transverse vibration is coming under beams. In the beams, what is the data needed? Deflection of the beams. Deflection of the beams. Okay. Okay, sir. Done. Okay. So you know the applications, right? This is in theory of machine vibrations. These three are in deflection, slope calculations. Right. Then these are studied in the strength of material, second chapter. Okay. Okay, sir. What are the types of beams? Two types, sir. Before that, you will see the supports. Students can answer. Students can answer. Right. In case of 3D, how many degrees of freedoms available? Students, please quick. You can answer through chat or you can tell the answer. Right. Quick. Number of degrees of freedom in case of 3D. Come on. This is too late. Either you have to chat or you have to unmute and tell me the answer. Anything. 6, sir. Very good. 6. Right. In case of 2D. In case of 2D. 3, sir. Very good. Very good. 3. 3. Right. So what are the 3 degrees of freedom? Ux, Uy, theta z. Ux, Uy, theta z. These are the 3 degrees of freedom related to 2D. Okay, right. So whatever the beams you are studying in your BE, particularly mechanical, civil up to 4th semester means, okay, for mechanical, full mechanical engineering, 2D. Okay. For civil, they may study 3D beams in the structure. They may study, I don't know. But in the strength of material, they are studying only 2D cases. Okay. Right. So we should be careful about 2D degrees of freedom. Right. What are the 2D degrees of freedom? Ux, Uy, theta z. Right? These are the 2D degrees of freedom. Okay. Right. Now, for calculating the support reaction, first of all, you should know whether the reaction will come or not. First, you have to confirm. Right? How to confirm, sir? These are the types of supports. All are 2D supports. All are 2D supports. What are the supports? Fixed support, hinged support, ball, roller, knife bed supports. Right. All are 2D cases. Right. If you are not permitting or if you are disturbing the UX, UX means what? Displacement in the X direction. If you are not permitting or if you are disturbing the UX, corresponding reaction will be developed. Corresponding reaction will be developed. Sir, if I am not disturbing, what will happen, sir? Reaction will not be developed. Reaction will be 0. Correct? Right. If I am disturbing the UY, vertical displacement, then corresponding RY will be developed. Okay, right. Otherwise, 0. Free displacement means 0. Sir, if I am disturbing the rotational degrees of freedom, corresponding moment reaction will be developed. Now, Ux is disturbed, sir, completely disturbed. So Rx will be developed in the fixed support because it is fixed support. Sir, Uy is disturbed, sir, completely disturbed. So Ry will be developed, sir. Right. Sir, theta is also not possible. It is completely disturbed. Okay. So corresponding MZ will be developed. Okay. Right. Okay. So our student Abhay is asking one doubt. Sir, if I am disturbing 70%, 70% I am disturbing, 30% free, 30% free, sir, free displacement. It means what will happen? Sir, 70% reaction will be developed. Reaction level is depending upon the level of disturbance. 100% disturbance, 100% reaction. Right? Okay. Clear. So for the fixed support, what are the reactions possible? Rx, Ry, Mz. All the three reactions will come. Next, hinged support. Hinged support. What happens to Ux, sir? See the support. Don't see the beam, remaining beams and all. Support. Only this region, right? Sir, Ux is disturbed, sir. It cannot move. So Rx will be developed. Okay. Right. Sir, Uy will be disturbed, sir. It cannot move up and down, sir. Ry will be developed. Okay. Right. Sir, rotation is free, sir. Free, yes, sir. Hinged means free rotation. Hinged means free rotation. Don't forget. Hinged means free rotation. So free rotation means moment reaction will be 0. It will not come. Okay. Moment reaction will not come. So value is 0. So how many reactions developed in the hinged support? Only 2. Next, ball support, roller support, knife edge. All are having the same type of behavior. Sir, what happens to Ux, sir, displacement? Easily it can move because they are resting on the ball or cylinder. Okay. So no resistance to the Ux, sir. Free movement. Okay. Reaction will be 0. Reaction will be 0. Sir, what happens to Uy? What happens to Uy? Sir, it will not move in the y direction. So Ry will be developed. Okay. Right. So our student is asking, another student, Gopi is asking one doubt. Sir, this beam will go up, sir. That is free movement, sir. That is okay, correct. But in general, beams are meant for carrying which type of load? Vertically downward load. In general. Correct? Is it correct? Answer please. In general, beams are meant for carrying vertically downward loads only. Correct or not? Yes, sir. Yes, sir. Right. So the beam is trying to move downwards, but the support is not permitting. So in that point of view, we are saying Ry is developed. Okay. Right. Okay, sir. Rx 0, Ry developed. What about rotation, sir? Sir, easily the beam will rotate because it is simply resting on the cylinder, freely resting on the cylinder. So free rotation means moment reaction 0. Okay. So this is very, very, very important in the examination point of view as well as in the interview point of view. Okay. So fixed support, 3 reactions. Hinged support, only 2 reactions. Ball roller knife edge, only 1 reaction. Okay. So one more information. Boundary condition. What do you mean by boundary condition? Terrific concept. Okay. In the industry, for example, if I am working in the ANSYS, I am not getting the answer. So I am going to ask help from the manager. So what manager will do? Immediately he will check the boundary condition only. Okay. If the boundary condition is wrong, I cannot get the answer or I cannot get the correct answer. Then what is boundary condition, sir? Is it a serious matter? Yes, sir. Matter is serious, but content is very simple. Correct? Sir, what is boundary condition? Known values of degrees of freedom. Known values of degrees of freedom. Okay. Unknown means don't say it is not a degrees of freedom. a boundary condition. Unknown means it is not boundary condition. Okay. Known means known degrees of freedom value is nothing but boundary condition. For example, here, what is the boundary condition? Sir, ux 0, sir. Uy is 0, sir. Theta is at 0, sir. Yes, correct. These are the three boundary conditions. Right. In case of hinge support, ux 0, uy 0, theta is at non-zero. So I cannot tell that. Okay. Then what about boundary condition in the roller support? Uy 0. Correct? Okay. So these are the fundamental informations. Okay. Right. While solving the support reaction, I told, right, 9 questions, possible questions in the beam. For everything, this is the ABCD. Okay. Right. Next, types of load. Sir, point load, sir. No need to do any kind of conversion. It is represented by capital letter W. Unit is Newton. Unit is Newton. Okay. Right. Then UDL. UDL. Sir, UDL is represented by two methods, sir. One is spring type pattern. Another one is this rectangular arrow mark. Sir, which one is preferred, sir? For us, rectangular pattern is preferred for us. Okay. So that we can study easily. Okay, sir. UDL is represented in the head of the UDL load in the question paper. In the question paper, they will say here, small w equal to 10 Newton per meter. This is the way they will tell. Okay. Right. But we are going to keep this small w as a height of the rectangle for our convenience. Okay. We are going to keep it as a height of the rectangle. Okay. Done. What is this length? This is not length of the beam. It is not length of the beam. It is length of the load. Okay. Right. Okay, sir. So UDL means load length will be available. Small w magnitude will be available. Okay. We have to convert the UDL into point load during moment calculation. Okay. And support reaction calculations. Okay. We have to convert. Imagine. We have to imagine the UDL as single equivalent point load. How to convert, sir? Sir, total load or single equivalent point load is nothing but area of the rectangle. Area of the rectangle. What is the area of the rectangle? L into B. Correct? L into B. It is nothing but small w into L. Okay. Right. Small w into L. Right. Capital W. Right. So at the centroid of the rectangle. Centroid of the rectangle. Where is the centroid? X bar equal to L by 2. Correct? Right. Okay. So this is the way we have to convert the UDL into single equivalent point load. Right. Next, UVL. UVL. So in the examination, UVL value will be given as a height of the triangle only. They will give. But our plan is also same. Okay. We are also planning to keep small w as a height of the triangle only. Okay. So we can keep as it is. No need to do any movement, location movement. Okay, sir. What is this length? Already you studied, right? Sir, this is not length of the beam. Length of load, sir. Very good. Right. As usual, total load, single equivalent point load, total load is equal to area of the triangle. What is the area of the triangle? Half BH. Half BH. Right. Half into B into H. So small w L by 2 is the equivalent point load. Sir, where it will act, sir? Where it will act? Again, centroid of the triangle. It will act at the centroid of the triangle. Okay. Sir, where is the centroid of the triangle? From the right angle end, L by 3. From the right angle end. Okay. Okay, sir. Next, couple, sir. Very famous one, couple. They will give one circular arc, arrow mark. Symbol will be M. Unit will be Newton meter. Repeated question, right? Simple question. No need to do any modification. Okay. Okay, sir. So types of supports, possible reactions, boundary conditions, types of loads we have seen. Next, see this concept. This is very important. This is used for moment area method. This is used for moment area method for slope calculation and deflection calculation. Okay, you know, I hope you know the importance of moment area method. Okay, so if you want deflection, one is direct formula. Second method is moment area method. Third one is Castigliano theorem. Fourth one is Maxwell-Betti reciprocal theorem. That's all finished. This is the way for calculating the deflection. Sir, double integration methods are conjugated beam methods they are not suitable for GATE exam. Okay, they are time consuming methods. Okay, if you see the previous year history, all the previous year deflection slope questions are asked based on these methods only. They never expect double integration method. They never expect the conjugate beam method. Okay, right. So this is easy. These methods are suitable for competitive examinations. Within 2 minutes, you can get the answer. Maximum 3 minutes. Okay, right. Okay, sir. So for the moment area method, this concept is required. Sir, what is the concept you have to observe, sir? Rectangle, full rectangle is there. Rectangle width B, height H. I am going to cut into 2 pieces. Okay, sir, with the help of this arc. What is this arc? Sir, it is a quadratic curve, sir. Parabolic curve. Okay, parabolic curve. So general formula is y is equal to kx power n. Okay, so I have finalized it is a quadratic, right? Because that is what we need in the strength of material. So this portion is semi-parabolic area. Right? So for the semi-parabolic area, what is the area, sir? 2/3 BH. Where is the centroid, sir? Centroid. This is a centroid. 3/8 from the right angle end. From the sharp end, 5/8 L. Okay. This is semi-parabolic area. Remaining area, sir. Parabolic spandrel. Okay. Right. Sir, what is the area, sir? BH/3. Half BH we are saying, right? Generally for triangle. This is 1/3 BH. Then X bar, centroid location is B/4. Right? So in the triangle, what we are saying? B/3. Now we are saying 1 order more, right? B/4. So these two are used for moment area method. In the critical situation, these two will help us. Okay, done, sir. Right. Anyone tell me where we are getting this shape in our strength of material? Tell me. Anyone, quick. Anyone knows, they can tell. Don't wait for others. No one knows. Very bad. We are at the end. We are in the January, right? One student answered. BMD of which case? Correct. BMD of which case? BMD of cantilever with the full UDL. Okay, very good. That's what I need. Okay, very good. So BMD of cantilever with the full UDL. This is the BMD, sir. This is the BMD shape. Okay, right. Where we are getting this geometry? Tell me. Similar answer. Where we are getting this kind of geometry? Semi-parabolic. BMD. I will give clue. BMD of simply supported beam with the full UDL. Okay, this is half of the diagram. Actually, full diagram will be like this. Okay, right. So I have shown only half. So BMD of full simply supported beam with a full UDL. Right? Right. This one. Right. So these two are the frequently asked question. In the examination point of view, this is very, very, very important. For so many of your seniors, this diagram helped them. Okay. Right. So I will show you. Directly I will show you. Where, sir? See, this is a cantilever with the full UDL. Correct? This is your BMD. What is the name of this geometry? Sir, parabolic spandrel, sir. Parabolic spandrel. Next, simply supported beam with the full UDL, sir. Correct? This is the BMD. This is the BMD. Sir, what is the shape? Sir, this is the semi-parabolic area. Semi-parabolic area. I want only semi-parabolic area for the moment area method. Okay. Right. So these are the very important applications. Okay. Now go back where we are studying here. Okay. So you know the importance of this. Okay. Right. If you want, you can take the screenshot also. Right. Okay. Next. Sir, types of beams, sir. Interview question. Interview question. It was asked for me also. Right. At the end of my PhD. Okay. Sir, statically determinate beams, statically indeterminate beams. For both civil and mechanical, only statically determinate beam is in your syllabus. Only statically determinate for both civil and mechanical in the SOM. But for only for civil, only okay. At mechanical, don't worry about the indeterminate. Okay. Now, statically determinate means what, sir? Right. If you are able to calculate the unknown support reaction with the help of equilibrium equation only, they are called as statically determinate beams. Example, sir, how many unknowns are here? Sir, three unknowns. Three unknowns. Okay, three unknowns. Sir, 2D beam. How many equilibrium equations are in your hand? 2D. 3, sir. Summation of fx equal to 0. Summation of fy equal to 0. Summation of mz equal to 0. Okay. So 3 unknowns, 3 reactions. Okay, sir. Done. Clear. We can do. Sir, here 2 plus 1. Correct? Unknown support reactions. Hinged support, 2 reactions. Roller support, 1 reaction. Totally 3 reactions. We have 3 equations. We can solve. Sir, overhanging beam, double side overhanging or single side overhanging, anything. Okay. Right. Sir, hinge, 2 support, roller support, 1 reaction. Okay. Right. So totally 3 reactions, 3 equations. So we can solve the support reactions with the help of equilibrium equations only. Okay. They are statically determinate. Come to right hand side. Fixed beam. Totally how many reactions? Tell me. Anyone? Quick. Type. Totally how many reactions? Sir, 3 plus 3, sir. 3 plus 3. How many equations in your hand? Sir, I have only 3 equations. We cannot solve. Okay. Here, 3 plus 1, sir. 4 unknown reactions. Equations 3. We cannot solve. Sir, 2 unknown, 1 unknown, 1 unknown. Totally 4 unknown reactions, sir. But equations only 3. We cannot solve. So what to do? We cannot solve now. We cannot leave it. Sir, I want extra helping equation, sir. Extra helping equation. So that I can solve the unknowns. Correct? So the extra helping equation is nothing but deflection equation in case of beams. Sometimes in the uniaxial bar also statically indeterminate case is available. In case of uniaxial bar, if the situation is statically indeterminate, who will help? Who is the additional helping equation? Sir, deformation equation, sir. Del L equation. Del L equal to PL by AE, right? That deformation equation will help in the one dimension uniaxial statically indeterminate bars. In case of beams, deflection equation will help additionally. Okay. Right. So it is a difference between statically determinate, indeterminate beams. Okay. Right. See, if you want me to slow down, tell me. Okay, I am thinking that already you have studied. Just we are refreshing. That is why I am telling quickly. Okay, if you want me to slow down in any locations, you can tell me. Right. Sir, this is statically determinate or indeterminate? Tell me, anyone. Statically determinate or indeterminate? Tell me. Answer. You can tell, unmute and tell, no problem. Determinate or indeterminate? Just now I have shown, right? So statically indeterminate. Sir, this is a statically indeterminate case, sir. According to syllabus, no. But they are asking. They are asking. It is asked more than 10 times for both departments. Why, sir? See, this case can be treated as cantilever with the point load at free end. Correct? Then UDL load. Correct? So this support reaction, right? Roller support means only one reaction will come. That reaction, then we can ask the same question in the SOM. Okay. Sir, at equilibrium, what is the support reaction? Is the question. Frequently asked question. At equilibrium, what is the support reaction at the free end, sir? Propped support, sir. Okay. Sir, equilibrium means what? No change in state. No change in state. It means, sir, UDL is creating the downward deflection. Correct? This point load is creating the upward deflection. So both quantity or magnitude of deflection should be equal. Direction will be opposite. Correct? So downward deflection due to UDL should be equal to upward deflection due to point load. Correct? If you are comparing these two deflection formulas, these are the deflection formulas. Right? You will get the support reaction RB is equal to 3/8 WL. It is a standard answer. It is a standard answer. Okay. So you should not calculate this in the examination. Time waste. Okay. It is a standard answer. Okay, sir. Okay, right. Okay. So far we studied the basics for the beams only. Right. Now we are going to start our work. Which work, sir? Shear force diagram, bending moment diagram. Then next, bending normal stress, transverse shear stress, deflection, slope, everything you will study. Okay. Right. Okay. Sir, shear force diagram or bending moment diagram. For those two, right? I am going to give small special information. Means our rules. Okay, it is our rules. We must follow the rules. Okay, right. Sir, what is the rule? I will tell one by one. Okay, right. First, sir, what is shear force? Shear force at any section of the beam. Shear force at any section of the beam is the algebraic sum of all the forces acting from any one end up to calculation point. Sir, whenever we are seeing the word algebraic, it means we have to consider sign. Sign should be considered. Right? Right. See what they are saying, sir. I want shear force in this location. I want shear force in this location. Sir, go for algebraic sum of forces from any one end. Sir, this end, yes, we can do algebraic sum of 3 forces. Or from this end, yes, sir, we can go for algebraic sum of 2 forces. Answer will change or not? It will not change. Okay, right. See the sign convention. Sign convention very, very important, right? This is a calculation point. Okay, or this is the calculation point, or this is the calculation point, or this is the calculation point. So there are 4 chances. 4 chances for calculation points. Okay. So let us imagine the original beam. This original beam is going to shear. Okay. If it is undergoing this type of shear, okay, this is called as positive shear. Positive shear. Correct? Sir, how to identify positive shear in the original question, sir? Because in the question paper, they will not give this kind of diagram. Okay, right. Sir, see here. This is the calculation point. If it is a calculation point, right side force, right? Right side force is downward. It means positive. Positive. So right side down is positive. That's all finished. Okay. Right. So out of 4 chances, we have to remember only one. This is enough. Right side down positive. It give four results. Correct? Right. Can you tell me the remaining 3 results? Sir, right side down. Right side down positive. Correct? Right. Okay. Then what is right side up? Right side up. It will be negative. Correct? Okay. What is the another meaning of this? What is the another meaning of this? Sir, right side down or left side up, sir? Left side up. This is also positive. Correct? Right. Sir, this is right side up. It means left side down. Left side down. Negative. Right. So 4 results will come. So we have to by heart only this. Only this. Right side down positive. Right? Okay. So anyway, we are going to do the questions, right? By the time you can understand. Simple case, right side down positive, enough. Okay. Shall we do the calculation here? So our student is having a doubt, right? Sanjay is asking doubt. Which doubt, sir? If I travel in this direction, answer will come, sir. He has doubt. We are going to check it. Okay. So where is the calculation point? This is the calculation point. Just right side of the C. Just right side of the C. Okay. Okay, sir. Left side up plus 35. Right. Then left side down minus 10, sir. Minus 10. So what is the answer in your calculation point? Plus 25. Okay, right. So we will check for the right hand side. Okay, so you are standing here. This is right side up, negative, minus 25. Then this is right side down, plus, sir, plus 30. This is also right side down, plus 30. Okay, clear. Same, plus 25. So now we are believing. What we are believing? Either we are traveling from right end or left end, answer will not change. It is confirmed. Okay. In the examination, we should not have this kind of doubt. Okay. Then what about bending moment at any section of the beam? Sir, same pattern, sir, same sentence. Bending moment at any section of the beam is the algebraic sum of all the moments acting from any one end up to calculation point. Sir, only one word is changed, sir, from the previous definition. What is that? Algebraic sum of all the moments. Previously, it was all the forces. Okay, right. Okay. So, sign convention, very simple. This is a calculation point. Either your left hand side or right hand side goes up. It is called as positive bending or sagging. Sir, it is your calculation point. Either your left hand side or right hand side goes down. It is called as negative bending or hogging. Okay. Right. So regarding the sign convention, we must follow the same sign convention for bending moment. We must follow throughout the world. But shear force, regarding the shear force in some of the books, this is given. In some of the books, the opposite is given, right? Because the reverse of shear force effect right? And current this method, shear force effect, they are same. Okay. Right. So shear force effect will not change even if you consider in the reverse way. But bending moment is very, very sensitive. Right. Sir, if it is bending upward, which type of stress will be developed here? Tell me, anyone quick. Which type of stress? In this location, quick answer. Sir, compressive, sir. Very good, very good. Compressive. In the bottom, tension, sir. Suppose if you are assuming in the reverse way, right? Sir, this is tension, this is compression, sir. Correct? Right. Now, one interview question. Sigma is equal to plus 10 minus 100 megapascal. Data. Sir, which is danger, sir? Which is danger? Which is critical? Plus 10 is critical. Reason, correct answer. Reason. Sir, tensile stress is creating the crack propagation, crack growth. Okay, crack propagation or crack growth. But compressive stress, it will try to close the already available surface cracks. Okay, so compression is not a critical one. Tension is a critical one. Okay, it is an interview question. It was asked for me also during my GE interview. Okay, it is a regular question. It is asked for many students. Okay, right. Okay, so tension compression is not equally treated in case of bending normal stress. So bending moment sign convention is a sensitive one, not like shear force. Okay, sir, done, sir. Shall we do the calculation, sir? Here, this is a calculation point, right? Shall we do the calculation from the left hand? Okay, done. Left hand, sir, 35. Sir, upward movement, sir. Positive bending. Plus 35 into 1. Distance is 1 meter. Okay. Then what is the moment due to this force? Sir, 0, sir. Why? Already I told this is at negligible distance. Negligible distance just to right side of the sea. Correct? Okay. So that is 0. What is the moment? 35 plus 35. Okay. Now go to right hand side. Upward bending plus 25 into 2 meter, 5 meter, 9 meter. So plus 25 into 9. Correct? Plus 25 into 9. Okay. Next, this is downward bending. Minus 30 into 5 meter. Minus 30 into 5 meter. Correct? Right. Next, minus, it is also downward bending. Minus 20 into 2 meter. Right? Minus 20 into 2 meter. If you calculate, we are getting the same number, sir. We are getting same number. Okay. Now you are believing, right? Either you are calculating from the right hand or calculating from the left hand. SF or BM value at any location will not change. Are you believing or not? Answer, please. Answer quick. Now, are you believing? Right side calculation or left side calculation? Yes. Okay. Right. Okay, sir. Next. Now I am going to give the rules. I told I am going to give one rules, right? One set of rules. What is the rule, sir? What is the rule? See here. This is the calculation point, right? Okay. Now, for drawing the SFD, first of all, we have to identify the key locations. Key locations. It means where you are going to calculate the shear force. Right? Sir, what are the key locations, sir? Key locations. See here. This is a key location set for SFD. Right? We must follow the rule. Right? Otherwise, for simple cases, you can give the answer. For the GATE exam question, you cannot give the answer. Right? Okay. If you are following the rules, whatever may be the tough question, you can challenge. Okay. Right. Okay, sir. SFD key locations. Support. Right. Location of point load. Start of the UDL, end of the UDL. location of couple. Okay. So these are actually, this is not having serious effect. Anyway, we will do it. So these are the key locations. These are the key locations, right? Okay, sir, what is the use of key location, sir? For example, this is a case, right? How many key locations available totally? Sir, 1, 2, 3, 4, 5. Correct? 5, right? Okay, sir. 2 support, 3 point loads. Right? Okay, fine. I am going to add one UDL here. Now tell me how many key locations? Sir, same 5, sir. Same 5. Why? Sir, start of the UDL and point load both are lying on the same location. It means single count. It means single count. Don't repeat. If 2 key locations are lying on the same place, single count. Okay. Similarly, end of the UDL and support reaction both are lying in the same place, so single count. Correct? I hope you understand. Okay. Okay, sir. What is the use of identifying the key locations? Number of key locations. Here you told 5 key locations, right? Yes, right. For every key location, we have to calculate 2 readings. Single key location, 2 readings. How, sir? In the single location, how can you find the 2 readings? See here, one reading is just before. How much distance before? Negligible distance. Correct? Another location is just after. Just before, just after. Correct? Okay. Right. Sir, answer will change. Yes, surely answer will change. Right. Suppose I am asking one question to you. I am standing here, calculation point. How much force is in my right hand side? How much force is in my right hand side? I am standing here. Tell me the answer. How much force is in my right hand side? Sir, 0, sir. 0. Right? Now I am going to stand just before. Now tell me, how much force is in my right hand side? How much force is in my right hand side? Sir, minus 25 Newton, sir. Minus 25 Newton. Right side up. Correct? Minus 25 Newton. Correct? I am standing here. In my right hand side, one force is available. The value is minus 25 Newton. Upward force. Right side up. Right? So this is the way, just before, just after, calculation should be done. Okay? Right. Okay. So I will show you some samples, standard cases. Right. Only standard cases. Already I have done. Cantilever with a point load at free end. Cantilever with a full UDL. Right. Cantilever with a couple. Cantilever with a couple at the free end. Simply supported beam with a central point load. Then simply supported beam with a full UDL. Correct? These are the 5 cases. Cantilever 3 cases. Simply supported beam 2 cases. So all the 5 cases are must one. Okay. You must fully study the 5 cases. Right? Okay. Then special cases. This is a special case. This is a special case. Okay. Now, how many key locations available? Tell me. How many key locations available? Quick answer, please. Quick. 4 key locations. So how many readings should be taken? How many readings? How many readings required? Either for SFT or PMD, same concept. How many readings? One key location are 2 readings. Just before, just after. 8 readings, sir. I want 8 readings. Correct? Right. I want 8 readings. See the reading, sir. Reading number 1, reading number 2, 3, 4, 5, 6, 7, 8. 8 readings. Correct? Completed. Diagram is completed. Okay. Next, bending moment. Sir, how to find the bending moment key location, sir? Same type, no. Come to the previous one. Sir, these 4 for SF, these are the 4 key locations. These are obtained from the given question paper diagram. Given question paper diagram. Similarly, the first 4 are taken from the question paper for BMD. In addition to that, after drawing the SFD, we have to check whether zero shear force. It means shear force is crossing from positive side to negative side. Shear force is crossing from positive side to negative side. If it is crossing, that is called as zero shear force location. Sir? Why are you focusing that point? In that location, we will get maximum bending moment. Okay, sir, this zero shear force is obtained from the SFD only. After drawing SFD only, you will come to know that kind of zero shear force location is available or not. Okay, right. So 2 type of key locations. One is from the given question paper. Another one is taken from the SFD. Correct? For BMD. Okay, right. For BMD. Now come to this case. Sir, how many key locations for BMD, sir? Sir, same 4, sir. Why? Sir, bending moment is changing from positive side to negative side, sir. Then you can add the key location, sir. No, sir, I will not add. Reason, sir, this is the location, sir, zero shear force. This is the location, sir, zero shear force. But already this location is counted. This location is counted for point load. Correct? This location is counted. So recounting should not be done. That is why I am saying for BMD, again, same key locations, 8 readings. Sir, 2 readings, sir. 2 reading. If I give a dot mark and circle means both readings are same. Both readings are same. Right? Okay. Done. So 2 readings, 4, 6, 8. 8 readings are available. Okay. Sir, you told one special, it is a special case you told. What is a special? Sir, in a particular region, shear force is 0 for a particular length. Right. In that location, bending moment is constant. Okay. Right. Sir, the situation, bending moment without shear force. Bending moment without shear force is called as pure bending. Bending without shear force is called as pure bending. Sir, it is a special, sir. Yes, it is very, very, very important. Okay, special. It is special. Sir, in what way it is special? What is pure bending definition? Bending without shear. Correct? Sir, this definition is in terms of phenomena. Okay. Next definition. Sir, what is a load? Bending moment without shear force. Correct? Okay. In terms of load. Next, I want definition in terms of stress. Sir, which stress is developed due to bending moment, sir? Sigma B. Right? Then which stress is developed due to shear force? Tell me, which stress is developed due to shear force? Tell me. Come on. Anyone? Quick. Which stress is developed by shear force? Don't say shear stress. Don't say shear stress. If you are asking the ECE student or EEE student, they will say shear stress. Sir, shear force is creating shear stress. Sir, no, okay. For ECE, EEE, computer science students. You are mechanical civil students, right? Tell me correctly, correct name. Transfer shear stress. Very good. Very good. Okay. This is transfer shear stress. One more shear stress developed by shear force. One more shear stress developed due to shear force. Tangential. Correct? Tangential shear stress. Okay. Only two shear stresses will be developed by shear force. Right? One more shear stress is available. Torsional shear stress. That will be developed by torsional shear stress will be developed by torque, sir. Torque. Okay. So hereafter, don't use the word shear locally. Don't use shear stress simply, right? So if you have to tell correctly, sir, transfer shear stresses are tangential shear stresses are torsional shear stresses are, because all the three stresses are having different load, different pattern, different formula. Okay, right. Okay, sir. Different side effect also. Different side effect also. Okay. Okay. So this is tau transfer. Okay. So sigma B without tau transverse. Third definition. Pure bending, third definition. Next, simple definition. Sigma without tau. Sigma without tau. Okay, right. Sir, you are all, our students are seeing one component. Okay, there is a shaft, you can say, shaft. Okay, it is loaded with a different type of loads. Right? You are seeing that normal stresses are available without shear stress. Normal stresses are available without shear stress. It means shear stress is not available, right? Only normal stresses are available. Now I am asking one question to you. Can you give the new name for the available normal stresses? Can you give the new name, another name, or rename that normal stresses? Shear stresses are not available. Okay. Normal stress available, right? Can you give the another name, new name? Anyone, quick. Principal stresses. Very good, very good. Okay. So the normal stresses without shear stress is called as principal stresses. Okay. Principal stress state. So pure bending is a principal stress state. Correct? Huh? Okay, right. Can you draw the more circle for pure bending? Mechanical students, can you draw the more circle for pure bending? Yes or no? Answer yes or no. Yes, sir. Yes. Already you have drawn in your classroom. Okay. In front of me, you have drawn more circle for pure bending case. Okay. Right. So I believe you can do. Okay. Right. So the special name given for this arrangement is 4-point bending or flexural test. It is a ASTM approved test. ASTM approved test. Okay. Pure bending. One more pure bending is available. One more pure bending. Okay. Right. Which one? Which case, sir? See this case. Cantilever with a couple at the free end. SF. Sir, this is a SF, sir. Where is the diagram? Sir, shear force is 0, sir. Throughout the length, shear force 0. Right? Then bending moment, sir, bending moment is constant, sir. Bending moment is constant. So bending moment shear force 0. It means it is pure bending. So pure bending means you know the meaning, right? Shear force 0, bending moment is constant. Bending without shear, bending moment without shear force, sigma b without tau transverse, sigma without tau, principal stress state. Correct? Right. Okay. Then main conclusions from the SFD BMD and the pattern. Okay. Now we are going to discuss. Right? Very important slide. Sir, point load. For the point load, SF value will be constant. SFD will be constant. BMD will be linear. Linear means what? Inclined straight line. Okay. It may be positive sir or negative slope. It is not a matter. Inclined straight line. For UDL, linear SFD, quadratic BMD. For UVL, quadratic BMD, quadratic SFD, cubic BMD. Right. For couple, zero shear force, constant bending moment. Correct? Right. See the order. This will come to this place. This will come to this place. Okay. Right. This table is very, very important. Clear? Right. Next, sir, this question is taken from the Beer and Johnson book. Beer and Johnson SOM book. Okay. So what we have done? See here. This is a main beam. This is a main beam. In addition to the main beam, there is a small welded L angle, L member, L bar. Okay. In the welded L bar, they are applying the load, point load. So first work is shift this load to main beam. Shift this load to main beam here. Okay. Sir, how to shift, sir? Shall I shift like this? Is there any change? Is there any change in effect? Tell me, answer please. Quick. Is there any change in effect? If I directly shift it up, is there any change in effect? Quick answer. Sir, no change. No change in effect. Okay. Effect will not change. Simple law of transmissibility. Okay. But we are not doing this method. Okay. We are not doing this method. Why, sir? Sir, if I increase the load, this instead of 400, I am applying 500, 600, 700, 800 like that. Okay. Where the effect of load will be developed in the beam. In this point, no, sir. No. Which point? Sir, D. At D only, the effect of 400 Newton will be felt. Okay. Right. So, we have to shift the 400 Newton to the D. Correct? Right. Sir, how to shift, sir? First, point load 400. Then, moment. Stand here. Go to this place, required place. Now, see this force. This is creating one moment also. How much? 400 into 0.4. Right. 400 into 0.4. Right. So first step is shift the load to the main beam. It is done, sir. It is done. Right. Right. Then we have calculated the support reactions. You can check it. Okay. We have calculated the support reactions. Right. Okay. Sir, why we are calculating the support reaction? For simply supported beam, support reaction is must. For cantilever beam, support reaction is not at all required. Okay, don't forget. Okay, sir. So for this, we have drawn the SFD BMD. All these data are given by the students only in my online class. Okay. Right. Now tell me how many key locations for SFD. Tell me how many key locations for SFD. Four. Right. Sir, start of UDL support 1. End of UDL 2. Couple point load 3. Support 4. Correct? Sometimes 2 key locations are overlapping. Overlapping na single count only. Right? Okay, sir. SFD is completed. This is a SFD. Where is the zero shear force? This is a zero shear force location. Zero shear force location. Now tell me, what is the count for key location in the BMD? For the BMD, tell me. For BMD, how many key locations? Same 4. Because this zero shear force location, right? This location is already counted, sir. Already counted. No need to redo the counting. Right? Okay. Sir, what are the special conclusions? Special conclusions. See the SFD only. See the SFD only. Sir, single location, but two different readings. Single location, two different readings. Single location, both are same reading. Single location, two different readings. Correct? Right. Now we are finding the root cause for this kind of two different readings in the single location. We are able to observe that, sir, due to point load, if there is a point load, two different readings will be there at the same key location. Just before, just after, both will change if the point load is available. Right? Sir, in this location, point load is not available, sir. Na? Both readings are same. Both readings are same. So we are going to conclude, sir, sudden jump. Sudden jump. What do you mean by sudden jump? Two different reading at the same location. Two different readings at the same location, a sudden jump will be there. Sudden jump in SFD is due to, tell me the answer. Sudden jump in SFD is due to which load? Quick, quick. Sudden jump in SFD is due to which load? Point load, sir. Very good, very good. Sudden jump in SFD is due to point load. Very good. Next, come to the BMD. BMD, right? Sir, same location. Both readings are same, sir. Both readings are same. Right? In this location, both readings are different. Here, both readings are same. Here, both readings are same. Now, we are having only one sudden jump. Only one sudden jump. Now, tell me, sudden jump, that is two different reading at the same location. In the BMD is due to which load? Tell me the answer. Sudden jump in BMD is due to which load? Couple. Couple. Okay, it is called as couple. So sudden change. Okay, right. Sudden jump. Two different readings. All are same meaning. Okay. So sudden jump in BMD is due to couple. Right. So don't forget. These are the conclusions. Correct? Read the point. Sudden jump. Two different readings at the same location in SFD is due to point load. Sudden jump. Two different readings in same location in BMD is due to couple. At the location of zero shear force, bending moment will be maximum. Okay, right. Okay, sir. So we are ready to study the SFD, BMD, bending normal stress, transverse shear stress. Okay, right. Next, another point, very important point. Okay, so I will draw. For example, in this location, okay, in this location, 168 Newton meter, correct? 168 Newton meter in this location. So in that location, I am going to draw the cross section of the beam. This is the cross section of the beam. Right? Right. Okay, sir. This is neutral axis. Neutral axis. So already you said M is equal to 168 Newton meter. Right? Right. Now tell me where you are having the same 168 Newton meter. In the top point number 1, 2, 3, 4, 5, or this is 6 to 10. This is 11 to 15. Correct? 6, 10, 11, 15. At which point you are having the 168 Newton meter within the cross section. Okay. Tell me, where are you having that value? There is a very big beam. Okay. Right. So your manager has given this beam. Right. Right. So they have given the name also A, B, C, D. They are asking what is the bending moment at C? What is the bending moment at C? You are saying 168. Okay. Go to the cross section. Yes, sir. In that cross section, where is that 168? Sir, everywhere. Everywhere. Okay. Everywhere. So what is the conclusion? Bending moment will not change within the cross section. Bending moment will not change within the cross section. It will change from section to section, one section to another section. Okay, right. So bending moment may change along the length of the beam, along the length of the beam. Correct? Right. Not within the cross section. Not within the cross section. Similarly, shear force also. Shear force is constant for all the points within the cross section. Shear force will not change within the cross section. Shear force may change along the length. It means when you are jumping from one section to another section, shear force may change. But within the section, shear force is constant. Within the section, bending moment is constant. Get it? Important point. Based on that, we are doing the calculations. Okay. Sir, what is neutral axis, sir? What is neutral axis? What is neutral axis? Anyone? Quick. What is neutral axis? Sharp definition. Answer. Neutral axis definition. Interview question also. Come on, anyone can unmute and tell me. So neutral axis, zero bending normal stress. Okay. So that is the answer given by the student. Actually, based on the stress, we should not define the neutral axis because bending normal stress is zero. Right? Bending normal stress is zero, but transverse shear stress is maximum. So one stress is zero, another stress is maximum. So don't define the neutral axis with the help of stress. Then what to do, sir? Right. So you know, right? In the top surface, what happens to the length? Contract, sir. Contract. Reduces. What happens to the length in the bottom? Elongates, sir. Elongates. Right. Now tell me, what happens to the length of the neutral axis? Tell me the answer. What happens to the length? No change. Correct? Right. Now see the definition. What is neutral axis? Axis of zero deformation. This is the correct definition. Axis of zero deformation. No contraction, no elongation. Correct? Right. Don't explain with the stress. Suppose you are answering bending normal stress is zero, sir. Okay, that is not bad. Correct. But next question will come in picture. Then what happens to transverse shear stress? Transverse shear stress, that is maximum, sir. What is the pattern of transverse shear stress? Parabolic, sir. What is the transverse shear stress in the top? 0, sir. What is the transverse shear stress in the bottom? 0, sir. So many questions you have to answer, right? So neutral axis means axis of zero deformation. Don't forget. Sharp answer, right? So this is a bending normal stress pattern. Bending normal stress pattern. Okay, right. Correct? Right. So bending normal stress varies linearly from top to bottom, not from left to right. Okay, it is not varying from left side to right side, only varying from top to bottom. Okay, right. Varies linearly. Maximum at the top, 0 at the neutral axis, again maximum at the bottom. Correct? Okay, done. Then formula. See the formula slide. Sir, we are studying the bending normal stress in two views. Sir, Euler's bending equation. M by I is equal to sigma B by Y is equal to E by R. What is Y? See here. Suppose if your manager is asking the bending normal stress in this location, you have to ask, sir, tell me the distance between your required point, means calculation point and the neutral axis. Tell me the distance. I will give the sigma B in that location. Okay. Then what is Y? Distance between calculation point and neutral axis within the cross section. Okay. Distance between calculation point and neutral axis within the cross section. Okay, done. Wait. Sir, from these two, we are studying one track. Okay. From these two, we are studying another track. Okay. Both are asked in the GATE exam. Weightage, sir, so far in the mechanical engineering, only 2 questions are asked from this track. Okay. Right. All the remaining bending normal stresses are from left side track only. Okay. Done. Okay, sir. Okay. Sigma B equal to My by I. Sigma B is equal to My by I. General formula. This formula is valid for any point within any type of cross section. Sir, any point within any type of cross section, sir. This formula is valid. Sir, any type of cross section, square cross section, rectangle cross section, circular cross section, I section, T section, anything. Okay, right. Okay, sir. Sir, I want for rectangular cross section or square cross section. Correct? Right. Okay. Now tell me correct name for this I. Tell me the correct name for this I. Already we discussed in the class. What is this I? Very good, very good. Right? Sir, area moment of inertia. Don't say moment of inertia. Don't say moment of inertia. That is that will create angry. Okay. Right. Area moment of inertia. I should be started with the area or mass only. Starting word should be area or mass. Right. So this is area moment of inertia. Sir, when we have to use the area moment of inertia? Whenever you are hearing the word bending, twisting, buckling. Okay, which moment of inertia should be used? Area moment of inertia. Correct? Whenever you are hearing the word rotation, rolling, we have to use mass moment of inertia. Okay, sir. Done. Okay. Sir, for rectangular cross section, at outer surface, okay, outer surface y is equal to h by 2, 6m by bh square, maximum bending normal stress. Sir, top or bottom, sir, both, anything. Okay, right. 6m by bh square. For circular, sir, for circular cross section beam, what is the maximum bending moment? 32m by pi d cube. Okay, so video will be recorded. You can see the derivations later, right? Right. Then another information, sigma b is equal to my by I, right? So we are modifying m divided by I by y max. See, this I by y max is nothing but section modulus. Sir, what is the use of section modulus? For comparing the load carrying capacity of the beams. There are two beams, A and B. Which will carry more load? It is decided based on the section modulus. Okay. Sir, if the bending moment is given, we can go for this track. Sir, bending moment is not given. Here, bending moment is not given, but a rod is bent for this much radius. Okay, right. I think you have seen this kind of bending of rod in the construction site. Did you see this in the construction site? The construction site, building construction site. Sir, we are mechanical, sir. We should not see the civil building like that. Everyone would have seen, right? This bar bending, right? Bar bending. So here, the radius of the bending, radius of curvature of the bending will be given in the question paper. Sir, how much angle, sir? Either you are bending for 90 degree, or you are bending for 180 degree, or you are bending for 360 degree. It's not a matter. Answer will not change. Okay. So the amount of bending normal stress depends on this radius of curvature only, not the angle. Okay. So don't forget. What is the formula? See the topmost formula, main formula. Sigma B by Y is equal to E by R. This one, right? Okay. If you want sigma B max, Y is the variable. Okay. Y max. E Y max by R. Sir, what is the value of Y max? In case of rectangular cross section, H by 2. In case of circular cross section, D by 2. Correct? Okay. Any doubt? Any doubt in the bending normal stress formulas? My by I, 6m by bh square, 32m by pi d cube, Ey by R. Is it clear?
Sir, R is measured from which?
R is measured as a radius of curvature of the bending. Radius of curvature of the bending. From the center. Oh, you are asking whether from here or in the inner surface. That is a doubt.
Yes, sir.
Yes, yes. Inner. Actually, if you want accurate reading, we have to calculate for up to neutral axis. That is the accurate value. But in our strength of material, based on the previous mechanical engineering gate questions, IES questions, they are taking in the inner surface only. Okay, so we can also follow the same thing. Okay, your doubt is correct. Correct answer is up to neutral axis. Correct answer is up to neutral axis. But in the previous year questions, they have used up to inner surface only. Excellent doubt. Okay. Any other doubt? Any other doubt here? Okay, wa? Okay, sir. Now I am going to ask one question to you. You told you don't have any doubt, right? Come to this formula. From these three, how many parameters are varying within the cross section? How many variables? 3 variable, 2 variable, 1 variable. One variable. Which is the variable? Tell me. Your answer is correct. Y is variable, sir. Y is variable, sir. Correct. Very good. Now tell me, what is the definition for I? Okay, so we have to explain more. Correct? So I is nothing but so I will explain. I is nothing but area moment of inertia of the whole cross section. Very good, very good. Area moment of inertia of the whole cross section about neutral axis. That is the original definition for I. Okay. Area moment of inertia of the whole cross section about neutral axis. So whatever may be the calculation point within the section, I will not change. M will not change. Correct? Only Y will change. Okay. Okay, sir. Done, sir. Right. Next, we are going to discuss about transverse shear stress. Before going to the transverse shear stress, see this. This is which type of shear stress? Tell me. We are seeing two type of cross section: rectangular cross section and circular cross section, right? So due to the force, shear force, the beam is sheared off. The beam is sheared off, right? Now tell me which type of shear stress or which type of shear is developed? Sir, this is the shear area, shearing area. This is a shear force. Sir, shear force is parallel to shearing area. It means tangential shear stress. Tangential shear stress. Shear force is parallel to shearing area is tangential shear stress. Correct? Okay. Sir, what is the formula for tangential shear stress in the rectangular beam, sir? Sir, shear force V. V is shear force, right? Divided by shearing area BH. Shearing area BH. Okay. Sir, for circular cross section beam, what is a tau tan? Tau tan is equal to shear force V divided by pi r square. Correct? So don't forget this formula. V by BH, V by pi r square are the tangential shear stress for rectangular cross section and circular cross section. Okay. Sir, Euler beam, Timoshenko beam. Euler beam, Timoshenko beam. So Euler beam is assumed as a thin beam. Thin beam. Okay, right. So in case of thin beam, tangential shear stress will be developed and bending normal stress will be developed. The failure may occur due to bending normal stress. That is tensile stress in the bottom surface. Okay. Sir, if the beam is assumed as thick beam, okay. So due to the shear force, this kind of failure occurs. This is possible only when the thickness is high. Sir, what is this type of shear, sir? Shear between two adjacent layers. Shear between two adjacent layers is nothing but interlaminar shear or transverse shear. Why it is called as transverse? Transverse means perpendicular. Right? So shear force V is perpendicular to the shearing area. That is why we are calling it as a transverse shear stress. Okay. Sir, what is the formula, sir? So in case of Timoshenko beam, tangential shear stress possible, transverse shear stress possible, bending normal stress possible. Sir, transverse shear stress varies parabolically from top to bottom. Okay. 0 at top, maximum at neutral axis, 0 at bottom, sir. Right? Sir, what is the formula? Formula. See the formula for transverse shear stress. VQ by IB. VQ by IB. Okay. Right. Sir, that formula is valid for any point within any type of cross section, sir. Okay. Then come to the second box. Rectangular cross section. Sir, our beam is rectangular cross section. What is the transverse shear stress? It will vary from top to bottom, right? At any point, you can calculate this transverse shear stress. Sir, in between, I don't want any value, sir. I want maximum value only, sir. That is equal to, at neutral axis, tau transverse equal to tau max. 3/2 tau tan, 3/2 tau average. So tau tan is also called as tau average because tangential shear stress is constant or uniform within the cross section. Okay. So transverse shear stress is maximum at the neutral axis. 1.5 times tau tan for rectangular cross section beam, 1.33 times for circular cross section beam. Okay, wow. Right. Okay. So go through this video later. Then, sir, in the middle of the region, means nearer to the neutral axis, material is not taking severe load, sir. How do you say they are not taking load? Sir, see the load, sir. Yes, okay. They are not utilized properly. Material is not taking severe load. But see here, sir, transverse shear stress is not a critical one in case of isotropic material, sir. Transverse shear stress is serious in layered material, FRP layered material or laminated material. Okay, not for isotropic. Okay. So focus of this is very important. So what are you trying to say by focusing this region? Sir, materials are wasted, sir. What is the use of material, sir? Okay, remove it. Remove it. Remove this zone. Then small amount of material is enough. This material is enough to carry the transverse shear stress. Correct? Okay. Then we are getting the top flange and bottom flange. Which is taking the tensile load? Top or bottom? Simply supported beam. In case of simply supported beam, which is carrying the tensile load, critical load, bottom. So bottom flange is critical, sir. That is why we are keeping large bottom flange. Okay, right. So top flange can be small. Okay, small flange is enough so that we can avoid the stress concentration. Okay, right. Uniformly receiving the load. So that is why we are going the I section. So why we are going for I section? For effective utilization of material. For effective utilization of material, we are going for I section. Similarly, for the cantilever beam, in case of cantilever beam, where is the tensile stress? Top or bottom? Tensile stress in the cantilever beam, top, sir, top. Correct? Right. So top flange only is enough. There is no need of bottom flange because it is not going to receive load or it is not going to take the tensile load. So bottom flange is waste. So in case of cantilever beam, we are going for T section. In case of simply supported beam, we are going for I section. Okay. Right. Now see the modified sigma b and tau transverse diagram. Very important. Okay. Right. So this is the new neutral axis, sir. New neutral axis. Okay. Sir, width is varying suddenly. For example, this is 50, this is 10, again this is 100. Sudden changes are available. But see the bending normal stress pattern. It is uniform, sir. Bending normal stress varies uniformly from top to bottom. Why, sir? Bending normal stress formula My by I. It is independent of local width. Sigma B is independent of local width. Correct? Whether width is changing or not, sigma B will not depend on the local width. Right? Okay. See this triangle. This triangle and this triangle. Similar triangle. Both are similar triangle. Similar triangle or not? Yes, sir. Similar triangle. So from this concept, similar triangle concept, what are you trying to say? Sir, sigma C max by YC equal to sigma T max by YT. Correct? This formula. Similar triangle concept. Okay. Done. Right. Next, when the width is suddenly reduced, tau transverse will increase suddenly. Sir, how many times, sir? How many times it will reduce? Sir, if the width is reduced by 10 times, transverse shear stress will increase by 10 times. Okay. Right. So see the formula. Tau 3 by tau t equal to B2 by B3. Where is 2 and 3? See the 2, 3. Okay. Right. Okay, sir. This is enough. Similarly, modify diagram for T section. See the modified diagram for T section. Again, two informations. Bending normal stress is independent of local width. Transverse shear stress depends on the local width. Right. Then similar triangle concept. Sudden jump in transverse shear stress. Right. So that's all about support reaction, SFD, BMD, bending normal stress, transverse shear stress. Right. So next, what is our work? We have to do the calculation, sir. We have to do the calculation with the previous year questions. Right? Right. Okay. So any doubt? Shall we go for question? Go through this video slowly. Whatever the doubt you have, it will be cleared if you go through the video, because all the notes I have shown in the video, right? Shall we go to the question? Yes. Right. Okay. So there are a lot of questions. Whatever we discussed, right, today, shear force calculation, bending moment calculation, constant bending moment, pure bending case, shear bending normal stress due to curvature, bending normal stress due to bending moment, transverse shear stress, T section, I section, everything is already asked. Everything. Okay, right. So we will see the questions one by one. First question. This question. Read the question. It is I section, correct? Right. What is asked? Sir, find the magnitude of the shear stress in Newton per mm square at the web at its junction. Okay. At the web at its junction. Web means what? Sir, this is web. Actually, what is the correct name of this? Shear web. Because it is taking transverse shear stress, right? So at the web, in the web at its junction, it means junction. In this point only they want. Correct? Right. Okay, sir. Which formula? Sir, if it is rectangular section, circular section, go for individual formula. What is individual formula? Sir, 3 by 2 V by BH. 4 by 3 V by pi r square. If it is rectangular, circular, na okay. For T section, I section, we must go for VQ by IB. We must go for VQ by IB. Okay. So don't forget. Right? So tau trans equal to VQ by IB. Right? Okay. Right. For T section, I section, this formula only. Don't forget. Okay. So what is V? Shear force at the particular section. What is the shear force at the particular section? How much it is given? Quick, you have to answer. Question answer session is your session. Okay. Theory is my session. Shear force. Sir, 100 kilonewton, sir. 100 into 10 power 3 Newton. Okay. Then B. What is the B? B means local width at calculation point. B is nothing but local width at calculation point equal to how much? It is given, right? How much width? Quick. 10 mm, sir. Very good. 10 mm. 10 mm. V is ready, B is ready. So easy things are completed first. Okay, right. Next, I. Right. What is I? Area moment of inertia of the whole cross section about neutral axis. Correct? Right. So we have to go for parallel axis theorem for this flange and this flange. Correct? Is it correct? Parallel axis theorem. Yes, we have to go for parallel axis theorem. But there is another method. Since it is symmetric about x-axis and y-axis, we can go for full area moment of inertia. Full area. What is the full area moment of inertia? B 50 into what is the total height? 120, 120 cube by 12 minus this rectangular cross sections. Correct? Right. Minus B is how much? 50 minus 10 or 40. 40 into depth is 100. 100. BH cube by 12. Now tell me the answer. Tell me the answer. This is the area moment of inertia of the whole cross section about neutral axis. Tell me the answer quick. Try to use get calculator. Quick. Answer. Three 3.87 to 10 power 6. Right. Mm power 4. Mm power 4. What about others? Simply watching. Get exam is not a movie. We have to do work, right? Q. What is Q? What is Q? What is the definition for Q? I will explain first, right? Then we will come back to the question. Q. Q is nothing but moment of the area above the calculation point. Moment of the area above the calculation point. Sir, for force, we have calculated the moment. Okay. Moment of the area, yes. Area into distance. That's all. Okay. Moment of the area above the calculation point about neutral axis. So first highlight the area. Sir, this is the calculation point. Sir. What is the area above the calculation point? This green color dotted line, right? This is the area above the calculation point. Area above the calculation point. Okay. Then okay, sir. This is okay. Distance between center of the area, selected area, center of the selected area and the neutral axis, right? This is Y star. Y star. Area above the calculation point is A star. Correct? Right. So we are giving special name. Right? Area above the calculation point is A star. Distance between centroid of the A star and the neutral axis is Y star. This A star into Y star is nothing but Q. Okay. A star into Y star is nothing but Q. Okay. Right. Okay. Wow. So Q, what is Q? Moment of the area above the calculation point about neutral axis is equal to A star into Y star. Now come to the question. Where is the calculation point? This is the calculation point. What is the area above the calculation point? This area. Tell me area. What is A star? A star into Y star. A star is equal to 50 into 10, sir. 50 into 10. Okay. What is the Y star? Distance between the centroid and the neutral axis. Where is the neutral axis? This is the neutral axis. Okay. From here to here. This is Y star. How much? Tell me. 55, sir. Very good. 55. Now tell me the value. Come on, quick. A star, Y star. 27,500. 27,500. MMQ. Sir, all the values are ready. Right? Now substitute in the required formula. Right? Tau trans is equal to VQ by IB. V 100 into 10 power 3 into Q 27,500 divided by I 3.87 into 10 power 6. B 10. Right? Okay. What is the answer? Tell me. 71 megapascal, sir. Yes, sir. It's a 2013 question. 2013 question, right? I believe hereafter you will not have doubt on the VQ by IB. Correct or not? Shall I believe? Hereafter you will not do any mistake or you will not have any doubt on the usage of VQ by IB. Yes, sir. Yes. Correct? Clear. One question is giving the full calculation. Right? Okay. Next, See this question. It is IES question. A good question. Read this. They have given one I section, symmetrical section, right? So what is given in the theory? The shear stress at point P, very close to the bottom of the flange, is 12 megapascal. So where is the point P, sir? Sir, this is the point P. Correct? Right. Okay. 12 megapascal. The stress at the point Q in the web, shear web, very close to the flange. It means they are asking here. Right? Okay, sir. Which formula? Which formula? Tell me, give me the idea. Sir, here shear stress is given, here shear stress is asked. First of all, tell me, they are saying shear stress. They are talking about which shear stress? Tangential, torsal, transverse. They are talking about which shear stress? Sir, transverse, sir. Okay. Now tell me which concept is required. Sir, between the given point and asked point, width is suddenly reduced, sir. Width is suddenly reduced. Okay. So we have the special formula, sir. We have the special formula. Okay. So tau Q by tau P is equal to BP by BQ. Correct? Just reciprocal, inversely proportional. Okay. Now substitute the data. Tau Q is unknown. Divided by 12 into BP. BP is 100. Width 100. BQ is 20. Right? So 5 times. Then tau Q is equal to 5 into 12 equal to 60 megapascal. That's all finished. Okay. So 2 more questions. One line. But you should know this formula. Otherwise, chapter close. Right. 2028. Right. Okay. Next question. So this is for width reduction, width jump question. Right. Next question. Now, one question to you. Bending normal stress depends on the local width or not? Bending normal stress depends on the local width or not? No, sir. It is independent of local width, sir. Okay. We will see another question. See the question. IAS question. Right. It is a T section, right? T section is used in which type of beams? Tell me. T section is used in which type of beams? Sir, cantilever beams, sir. In the cantilever beams, top surface is subjected to which type of stress? In the cantilever beam, top surface is subjected to tensile stress. Okay. So keep all this point in your mind. Okay. While giving the answer. Now what is asked? Sir, the stress in the bottom fiber is asked. Right? What is given? . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . In the top fiber, sigma B is equal to 30 megapascal. In the bottom fiber, they are asking sigma B equal to question mark. Correct? Right. So this is tensile, right? Tensile. This is compression. Right. So which formula? Sir, similar triangle formula, sir. Similar triangle formula. Right? How to draw a similar triangle? So top surface tension, bottom surface compression. Okay, right. So neutral axis, this is a neutral axis. So what about this distance? Tell me, what about this distance? YC, sir. YC, very good. This is YC. Sir, what is the value of YC? Tell me, what is the value of YC? YC equal to 80. This 30 is equal to YT. Sir, which formula? Sigma C max by YC equal to sigma T max by YT. Correct? Right. So sigma C max asked, right? Sigma C max by YC 80 equal to sigma T max 30, YT 30. Now immediately we can give the answer. 30 by 30 na 1. So left side also should be 80 by 80. So sigma C max is equal to 80 megapascal. Correct? Right. Okay, done. So see the usage of formula. What is the main concept here? Sigma B is independent of local width. Correct? Okay, right. Now tell me the correct answer. Option A, C. Suppose if they are giving a plus 80, option E is plus 80, for example. What is the correct answer? What is the correct answer? C, sir. C is the correct answer. Okay, don't forget. C is the correct answer because bottom surface is compressive stress. Okay, next question. One question we will solve. All are different models, right? Now see the question. You see in the tomorrow's class, only questions will be there. Only questions. Okay. So you will try to solve at least 20 questions. Okay. Tomorrow we will plan. Right. Everything is of different variety. Shear force diagram, bending moment diagram, different models. Right. Because today we have seen enough amount of fundamental theory. Right. Sir, there are two statements given. member AB carries shear force and bending moment. Yes or no? AB is acting as which type of member? Tell me. AB is acting as which type of member? AB is acting as which type of member? Cantilever, sir. It is a cantilever. It is acting like a cantilever. Right? Right. So left hand fixed, right hand is subjected to point load W. Right. Now they are saying it is subjected to shear force and bending moment. Correct or not? Yes, sir. Because, sir, what is a BMD diagram? Triangle. SFD diagram. Rectangle. Correct? This is SFD. This is PMD. Correct? SF value 0, W, 0. SFD. Standard answer 0, 0, 0 minus W into L. Okay. Okay, sir. So first answer is correct. Second statement, member BC carries axial load and shear force. Sir, what is the load applied on the BC, sir? What is the load applied on the BC? See here, this is the BC, right? BC, BC, right? So how many loads are applied? Sir, 1 point load is applied, sir. Due to law of transmissibility, we are applying 1 point load. Okay. Okay, this is okay. Next, sir, one couple is acting, sir. One couple is acting. Clockwise couple or counterclockwise couple? Tell me. Clockwise couple or counterclockwise couple? How to identify? Go and stand in the calculation point. This force is creating clockwise or counterclockwise? Clockwise. Clockwise couple, right? Okay, right. W, let us say this is A or L, we can say L. This is W into L, correct? Now, this is the actual load. Now, they are saying axial load and shear force. Correct or not? Correct or not? Tell me. Axial load is okay, sir. Shear force is wrong, sir. When can we call it as a shear force? If the load is acting perpendicular to the main axis. If any force is acting perpendicular to the main axis, we can call it as a shear force. Okay. So A is correct, B is partially correct, right? Remaining false. A is true, 1 is true, 2 is false. Option A. Okay. Shall we do one more question? Small question. Very good question. Repeated question. Shear force is 0. SF equal to 0. Sir, this is correct or wrong? Tell me. This is wrong. This is also correct. This is also correct. This is also correct. Sir, I want one answer. Sir. I want one answer. Which is satisfying all the three. Constant. Correct? Right. So constant is satisfying maxima, minima, both principle. Okay. Right. Sir, what is the relation, sir? dm by dx equal to v. dm by dx is equal to v. Correct? Right. So we know how to find maxima, minima, right? For any function, right? So m is a function of x. Right? Equal to v. Suppose if the right hand side is 0, right? So dy by dx equal to 0 will give y max comma y minimum. Correct? Maximum, minimum. Correct or not? This condition is satisfying maxima, minima. Okay, right. Correct or not? Yes, sir. What is the general answer? General answer. Sir, if it is a constant, the differentiation will be equal to 0. Okay. Right. So the common answer is constant. Okay. Right. So it is satisfying both maximum and minimum. Okay. So slope is represented by shear force. Slope of the BMD is nothing but shear force in that location. Right. Slope of the BMD is equal to shear force in that particular location. Don't forget. Okay. So tomorrow, once again, I will discuss about this equation. It is available. It will take more time. Here it is available. So tomorrow we will discuss about this. Then again we will continue the questions. So tomorrow plan full of questions. Okay. Full questions. Okay. Any doubt so far? Any doubt so far? So today we solved questions for dm by dx equal to v, then similar triangle concept, then I section question, right? Then sudden change in width question, right? So all are different models. Okay. Any doubt so far? No doubt. Okay. So tomorrow we will solve the questions. Stresses in beams, SFD, BMD, bending normal stress, transverse shear stress. As a mix, we will solve it. Okay. Right. So thank you so much. Thank you.